Let's look at this one. Show that the integral of x squared plus x plus 1 over x plus 1, x squared plus 1 dx is 3 over 4 natural log of 2 plus pi over 4. So first we should break this into the partial fractions. So we have got x squared plus x plus 1 divided by x plus 1, x squared plus 1, and that should be equal to, this is a linear factor, and so it will just be a over x plus 1. But this is a quadratic factor, therefore this is going to be in the form bx plus c on top and then over x squared plus 1. And so in this way we're going to have x squared plus x plus 1 over x plus 1 and then x squared plus 1, and that is going to be equal to a x squared plus 1, we're just merging as a single fraction, plus bx plus c divided by everything divided by, you've got x plus 1, x squared plus 1. So the denominators are the same, therefore the numerators are going to be the same. X squared plus x plus 1 is going to be equal to a x squared plus 1. I've even left out x plus 1 this side because we're multiplying this and this. Okay, like that. Now at this point, I'll say let x be equal to negative 1, and I've chosen negative 1 because if I put negative 1 here, the whole of this term is going to become a 0. So if I put negative 1 here, negative 1 squared will simply be a 1. Negative 1 here, this will cancel with that, so we just have negative 1 squared, it will be a 1 if we put it here. So we're just going to have a 1 because negative 1 here will cancel out with the positive 1 there. And that is going to be equal to, if we put a negative 1 here, it will just be a 1. 1 plus 1, that is a 2. That will be 2a, meaning that a is equal to 1 over 2. Now, just from here, just from this stage which is here, I'm going to get x squared plus x plus 1 is equal to, we're going to distribute, that will be ax squared plus a, plus we distribute the bx plus c, that will be bx squared plus bx, and then plus cx, and then plus c. And so those terms which have got squares on the left hand side, we're going to compare the coefficients. So first we have got x squared plus x plus 1 is equal to, I'm getting those with squares, I factorize out the coefficients, that will be a plus b and then x squared. Those without any x squared but with x, there is b and c. So b plus c and then x, and then plus we've got a plus c. We've already found that a is 1 over 2. So if we get to compare this with this, the a plus b should be equal to 1. That means b is going to be 1 minus a, and our a is 1 over 2, meaning b is also 1 over 2. And if we get this one here, b plus c is going to be equal to the coefficient which is a 1, meaning c is going to be 1 minus c minus b, which is also 1 over 2, meaning c is also 1 over 2. So everything is 1 over 2. So let's hope we saw this form. Okay, this is the form. So we found that all the terms are 1 over 2. So we'll just go on and substitute. So this is going to be 1 over 2 divided by x plus 1 plus 1 over 2 x plus 1 over 2 divided by x squared plus 1, like that. Now that we've got this, we're now going to do the integration. So we are talking of the integral of x squared plus x plus 1 divided by x plus 1 x squared plus 1 dx, and we are saying this is the same as the integral of, this is the same thing, that is 1 over 2 divided by x plus 1 dx, and then plus the integral of 1 over 2x plus 1 over 2 divided by x squared plus 1 dx. Okay, we can also split it in that way. I've just removed the limit so that we just work with it in that manner, then we put the limits later. So what are we going to get from here? Well, that is going to give us, I can remove this constant outside, and then plus I can factorize out 1 over 2 there also. So there will be, what will remain is x plus 1. So factorizing out 1 over 2, we are going to remain with x plus 1. And then down we are going to have x squared plus 1 dx. So from here we are going to continue, and this will give us 1 over 2, the integral of 1 over x plus 1 dx plus 1 over 2, the integral. I can as well split this, so that will be x divided by x plus 1. Okay, and then plus 1 divided by, sorry, this is x squared, this is x squared plus 1 also, because the denominator is common, so that is why I've done it in that manner. And so this is going to give us 1 over 2, the integral of 1 over x plus 1, and then plus, now I'm going to also distribute the integral to both. So this is 1 over 2 integral, that is 1 over 2 the integral of x divided by x squared plus 1, plus also 1 over 2 the integral of 1 divided by x squared plus 1. Well, just something here, the question is saying this is pi over 8, not pi over 4. Okay, now I can put back my limits. This is 1, this is 0, this is 1, this is 0, this is 1, this is 0. So this is going to be 1 over 2. When I get the differential of 1 over x plus 1, that whenever we've got 1 over x plus 1, we'll just bring natural log, and we write what? We write the x plus 1. So that's absolute value, like that. And then we are going to write our limits. We have got 1 and 0 plus 1 over 2. We have got x squared plus 1 here. Well, for this one, we need to use the u substitution to be able to do that one. So I'll say let u be equal to what is in the denominator. So always get the higher power. So that is x squared plus 1. So du is going to be equal to 2x. In other words, du over dx is going to be equal to 2x. But I don't want 2x in the denominator. So I'm going to multiply everything by 2x. I mean dx, that means dx comes this side. So making dx a subject of the formula, that is going to give du over 2x. So that means before I find the integral, I need to substitute there. So this is going to become the integral. There is 1 here, there is 0 here, and then x, but where there is x squared plus 1, I'm putting a u. Okay, and then where there is, oh, I left out, I've been leaving out dx on all these. It's supposed to be dx, shouldn't be left out. Now where there is dx, that's where I want to put du over 2. We're not leaving out that because we are finding these derivatives with respect to x. I mean these integrals with respect to x. That's why I always put dx there. Now here I want everything to be in terms of u. That's why I'm putting du, because it's with respect to u. Now this is a 2x here because we are dividing both sides by 2x. Okay, and then we have got plus 1 over 2. Now for this last one, for this one here, when we talked about the the derivative of inverse trig functions, the derivative of tan inverse of x, we saw that it was 1 over x squared plus 1. So when you are going back, when you integrate this one, you are going to get back this one. That is the relationship, because integration is simply anti-derivative. It is just going against differentiation. And so therefore, the integral for 1 over x squared plus 1 is tan inverse of x. What are our limits? Our limits, we have got 1 and 0, like that. So we can see that this x can cancel out with this x. So what we are going to have here is 1 over 2. We have got a natural log of x plus 1, and we have got the limits 1, 0 plus. Now I'll bring these 2 outside. It will multiply with, because this 2 is in the denominator, it will multiply with this 2 in the denominator. That will be 1 over 4. And then we remain with the integral of 1 over u, and then du. This is all we're going to remain with limits 1 and 0. Now the integral of 1 over u, that will just be natural log of u. Whenever you've got 1 over, as long as it's not x squared plus 1 and some other terms, which we are going to discuss when we come to talk about some special derivatives. So such terms are, if you are not having something like 4 minus x squared, a difference of 2 squares, or a sum of 2 squares, or even in the opposite direction like that. If you are not having these, then you can go just direct and get to substitute. Now here we have got only u. So where we have 1 over u, the integral of 1 over u is always natural log of u. So that's why I just want to write direct here, natural log of u. But instead of me writing u, what is my u? My u is x squared plus 1. Well, I'm going direct and putting x squared plus 1. I didn't want to use it direct because for the direct one, it would have brought in some other principles, and that would have taken us to some other things. So I've just written, I first put u there, and then I found the integral of 1 over u. That gave us natural log of u. And then we've now substituted back our u, which is x squared plus 1. And our limits here, we have got 1 and 0, plus the last one, which is 1 over 2 tan inverse of x. Our limits 1 and 0. Now we can go on and substitute our limits. Therefore, this is going to give us 1 over 2. I'm going to substitute first the upper limit, which is 1. That will become natural log of 1 plus 1, which is natural log of 2. I was supposed to say minus the natural log of 0, but natural log of 0, if we can punch that, it doesn't exist, the natural log of 0. So plus, we also have 1 over 4 natural log. I'm also putting a 1 here, 1 squared plus 1. That will just be a 2, so that we have got natural log of 2. And then plus 1 over 2, we have got now the tan inverse. We are going to put a 1 here. Tan inverse of 1. Tan inverse of 1, that is a 45. 1 is a special angle. And 45, well, we are working radians because we can see a pi here. 45 is the same as pi over 4. I was supposed to say minus tan inverse of 0. We always subtract. But tan inverse of 0 is the 0, so it's not good writing that. So this is going to give us 1 over 2 natural log of 2 plus 1 over 4 natural log of 2 plus that to become now pi over 8. Now here what we can do is natural log is common on both, so I'm going to factorize out natural log. So this is going to be 1 over 2 plus 1 over 4, and then I'm going to put now natural log outside like that, then plus pi over 8. So 1 over 2 plus 1 over 4, that is a 3 over 4. And then we've got natural log of 2 plus pi over 8. So hence shown. That is what the question was asking about. Well, thank you so much for watching, and thank you so much for following up to the end. Please subscribe and continue enjoying the videos. Enjoy your day.